Okay, last time we did a bit of study of the coordinate transformations that you do when you do covariant and contravariant unitary vectors. We're going to do the same thing as we go here to discuss the Hamiltonian of this object. And the Hamiltonian has some advantages and disadvantages like almost any theoretical construct in physics, and we'll outline those. But the main thing I want to get across in the middle of this is the advantage of the Hamiltonian in that it has the time symmetry. By that I mean it has energy constant, and that is a very important thing for getting an idea of what we want for this system is to see how fast you can throw things, and that comes out after some algebra. Now, the actual calculation of equations of motion, the normal thing that we did fairly easily when we used Lagrangian, runs into a log jam. We kind of saw that was going to happen when we did the Hamiltonian with just polar coordinates and a single particle. It happens here in triplicate, so to speak. Anyway, after I get done doing the heavy part of this lecture, the last part of it in which we make a connection with kinematics, human kinematics of building our culture, but also recreation as modern humans enjoy. And the idea of having an approach to this and seeing a way to simplify, or at least make a model that you can solve almost visually, but certainly with sort of elementary algebra is an important part, I think, and a good skill to learn. So we'll start right away here just with the idea of the Lagrangian being converted to a Hamiltonian. So that's the main thing we're going to do for just the first part of this. So this is the last time we show that technique. We've already shown it in the review part of the course, but with a complicated system, this is the first go on that. So the idea here is that when you have a total differential of the Lagrangian, and remember it's kinetic minus the potential, we'll end up with a Hamiltonian that is the kinetic plus the potential, but that takes a little bit of doing. Here is the differential chain, including the possibility that the Lagrangian would have a external time dependence. That is, the idea that we're going to mess with this thing as it goes. So this is a general case of the first differential for Lagrangian, and we have here two coordinates, and there are two velocities. So this is double polar coordinates, if you will, but the idea is to have the connectivity. And we've already derived the kinetic part of the equation here, and given it in terms of the dynamic metric tensor, and the coefficients theta, 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 phi, phi, theta, and phi, phi are these four things here, and it is symmetric across diagonal. So putting this all together, and what we're really doing here is talking about the time derivative. The little dot here on the Lagrangian is that part, and we're writing each of the derivatives in turn, and that is the first step, really, of getting this into a Hamiltonian form. And the thing that we have so far are Lagrange equations 1 and 2. The partial derivative this is actually 1 right here, the partial derivative of L with respect to the velocity is a definition of canonical momentum. And then this Lagrange second equation here and and here it is the flip of that. That's the where the dot goes on the momentum instead of on the angle. And we got that for the other angle as well. And we also have now the partial derivative of L with respect to time exposed here. And if L has any explicit dependence, if that really is the case, then you've got that extra term. Of course, that's usually making it a very complicated thing. So if we consolidate this equation and basically rearrange it a little bit, we come up with an expression for something. That's this little combination here, which you should recognize right away as the Poincare or Legendre transformation sitting right there. That is the thing which will, if we don't have any explicit time dependence in the Lagrangian, or this thing right here, if we don't have that, then this will be 0, because the partial of L with respect to t would be 0. So this is the thing that makes the Hamiltonian, and that's what we're doing here. We define a Hamiltonian function for, basically this is sufficient complexity for this problem, but this is really all there is to it. There's nothing more that we have to talk about as far as this connection. However, it's worthwhile to go ahead and make the equations that we call Hamilton's equations. So the first thing we note here, jump this one ahead too as well, the first thing we note here is this total time derivative of h is equal to negative of the partial derivative of the Lagrangian. That's really quite a magical happening. The idea of that working for us is really important. But then we go back and just using the Lagrange equations and all of the stuff that we did in the review section, the functional dependence of Lagrangian versus Hamiltonian is now what we need to take advantage of. So the first one right here is that the partial derivative of this h here with respect to theta. Okay, well, there's nothing in here that is explicit in theta, so what I can do here is just say that's just simply the minus the partial derivative of L with respect to theta. That's the only term. And the partial derivative of L with respect to theta, that's the second Hamilton equation popping up there, is giving a second Lagrange equation here is giving that. So this is our first Hamilton equation for just the theta angle, and then there'll be a similar one for the phi angle. We go ahead here and look at the partial derivative of h with respect to the velocity of theta dot. Okay, well, you take a partial derivative of this, and then you get immediately p theta. So really, the first two Hamilton's equations are just sitting here right now. Partial derivative with h with respect to the velocity, well, that is definitely something that gets kicked out of here. The partial derivative of h with respect to velocity just goes to 0 due to the cancellations there. And it's the same thing for the phi angle. Now the equations, let's see if I'm making sure I have everything here. The 0th equation of the Hamiltonian that's crossed out here. I'm wondering, I put a lot of extra notes on this thing that don't seem to be showing here. I might have a different version then I thought, yeah, that one is showing that. This one is not. I wonder what that is. Here, we'll take a look at the center screen, because that's where I have this. The idea of the zeroth Hamilton equation, we already talked about that at length, that the Hamiltonian has to be independent of velocity, just like the Lagrangian is independent of momenta. So that's what comes out of this relation that we have right here. The idea is that this is the definition of momentum. Partial derivative of L with respect to theta dot is p theta, so we cancel between 0. But we knew that already. We knew that H couldn't have any velocity dependence at all. So that's Hamilton equation 0 for the coordinate theta. And then the next step here is doing it for phi. Same deal, partial derivative of H with respect to phi dot. We know that's a no-no, so we then receive immediately the Hamilton equation that involves a partial derivative with respect to p phi. That's velocity. It's kind of analogous, or a flip of what the Lagrangian does. Now I am noticing that this is the wrong version. Somehow I think I started here on this one with the wrong thing. So I'm going to back out of this just real quickly here, because we've got a lot of extra notes I've put in this thing that, let's see what I've got here. See, that looks like it should be.
Compare the sizes.
Yeah. Let me take a look at the thing here and see if I've got, that's it, all right. I wonder what is, okay. Well, we're going to have to rely on that one, because that's got the extra nuts. Anyway, let's go ahead and go back here and start her up again. Okay. Anyway, see if there go. I think this one. We'll take a look at. Okay. The main thing that remains to do here, we're doing that on all of these. I'll put this one up there to have. I think this one has all of the equations properly denoted. So I'll just leave that one up for the time being. Those are the expressions for every equation that we have already derived just with polar coordinates, but this is for a more complicated case. So obviously you have twice as many equations in the thing. Just wondering why this is.
Can your airport file share it over? We'd kick that off and let it happen.
Yeah, we could. Actually, it doesn't look as bad as I thought. That seems to be right. So we'll go ahead and use this. It's that part where we do the algebra of the Hamiltonian I'm worried about, because that had a lot of new stuff in it.
Copy it over, Bill.
We'll go ahead here. Anyway, this is simply taking the things that the Lagrangian has given us, and this is the Poincare-Legendre relation, which we're going to make use of in a funny kind of way today, and the Hamiltonian being written this way, and it's asking us to subtract the kinetic energy at this point. So we're using that expression for the kinetic energy. That's this guy up here immediately. And the result is that this expression right here is the same as this one right there. And this one's got a half in front of it, so we end up with 1/2 of all that, which is the kinetic energy. But you see, the result has been, since we subtracted Lagrangian, which had a minus phi, we got a plus phi. So that is correct numerically, But remember, H does not work differentially as a function of velocities. So they have to be cleared out and turned into momenta. And that means that we have to replace the covariant expression here, which gives the covariant metric and velocities. What we need is a contravariant metric tensor, which is the inverse of the covariant. So basically, 2 by 2 inverse is no problem. Remember how you do that. You switch the diagonals, change the sign of the off diagonals, which happen to be equal in this case because the metric is always symmetric. But that then has to be divided by the determinant of the original covariant metric. So this is the thing that causes the Hamiltonian to have an algebraic logjam for most applications. Simply because derivative of a fraction gives you powers of the denominator that make it much more complicated. So we have to turn this into an expression that involves the contravariant metric. And that we've already shown a little while ago, and that's a note that I think I had on this, that simply this is exactly and correctly formally correct, as well as numerically. So, because Hamiltonian must be explicit in momentum. Okay, so when you do that, this is what you're going to be getting right here for this Trebuchet equations. The Hamiltonian is what we'll be working with. Okay, let's see if there's anything else in this. Okay, the logjam. Okay, start making the equations for this. I'll go ahead and leave that one alone for a while. Making equations for this doesn't seem to be too difficult at first. I just have to use contravariant expressions for those, and the derivatives with respect to coordinates, either theta or phi, come out pretty nicely. That doesn't turn out to be too difficult, although writing it out is, as you keep using, actually taking the thing and putting it in the form that involves the momenta, that's what you get. So this makes a big mess, which I'm not going to bore you with. Obviously, I should be getting the same equations of motion from my Hamiltonian formalism as the Lagrange, but you've got to go through a lot of trouble to get that. So I make the point now that the elegance of the Hamiltonian is not found in the algebra for the equations of motion. As I said, we've seen this before just with polar coordinates of a single polar angle. So now what I'd like to do here is do a coordinate transformation, and that's what the Hamiltonian is really good for. Good for handling symmetry problems. And what we're going to do here is define a new kind of angle, which I call the beam relative angle. You remember that before, all of our angles, the ones for the main throwing arm, that's theta, and the angle that's theta there as well, if you have a perpendicular to the end of the throwing arm. But what I want to do is make the angle that drives this, which used to be this right here, had an angle that went right to the laboratory. That is, this is the laboratory or star-fixed coordinate. This is relative to the z of the laboratory. But I want to do a beam relative angle right here. And that turns out to simplify this equation so that we can actually get dynamics out of it. We already have the energy as constant. What we're going to be getting here is something that allows momentum, a new kind of momentum. We got to find that. Where is that new momentum that we would normally get? So what I'm doing here is defining this beam relative angle, and put a little b on them to indicate that. And the lemma 1 definition, that is, we're going to have a Jacobian to transform the original angles that we used, theta dot and phi dot, here to the velocities. These are velocities, and these are too. And remember the lemma 1 definition, that is, lemma 1, this is back in lecture 9 or lecture 14. The idea was that the Jacobian for the coordinate transformations has to be equal to the Jacobian for velocity. So that's, you only need one kind of Jacobian if you're only talking about first derivatives. And in this case, that comes out to be this, right here, partial derivative of theta b with respect to theta is just 1. With respect to phi is nothing. And then the phi b line right there gives you minus 1 and 1. Okay. So this is an example of a coordinate transformation that involves, well, generalized curvilinear coordinates of the worst kind. And this inverse of this as well, same thing. I could get the old velocities in terms of the new simply by getting the other thing. This is partial. If you can take a partial derivative of the coordinates, you get that immediately. And such a simple linear thing here that's no problem. So we just get this result there. Now, what I want to do is point out that when you're messing with these variables, you really have to be careful to get the right momentum. Because one of the things that is part of this is the first part of the Legendre transformation, this old momentum theta, old momentum phi, old velocity theta, and old phi velocity. Those products summed up have to have the same form as these new guys. Okay, so that's essential, and this happens automatically if you use the coordinate transformations that we were talking about, covariant, contravariant. So that's what I need to show, and that is coming up here. Yes, this is it. So this at least has that much new stuff that we need to talk about here. So here's the thing that's going on. The idea is, and this is something that I had, when I did it before, I always knew this, and so I just wrote it down. The momentum transform is always the transpose inverse of the coordinate transform. But if you do the covariant and contravariant analysis, that comes out automatically. So that's what this is. Now this is what we talked about. Some of you weren't here for the 14th lecture. On page 98 of the 14th lecture, the contravariant velocities here being transformed in on that page to a barred set of coordinates. Okay, in other words, here's good old phi dot and theta dot, and then here's the beam phi dot, beam relative phi dot, and the beam relative theta dot. Okay, so I put little bars over the top when we talked about this in the last lecture. And the idea of this is that you just, as I say, call it the chainsaw sum rule, where you hack this thing apart, slide them apart, and then you stick in a sum, these are repeated indexes, M bar here, for a Q bar that's a different set of coordinates entirely. Here they're just these things, being relative. And that, I think it's nice that B stands for beam relative here, it stands for bar down here. And the covariant definition of covariant contravariant unitary vector is this.
And we see right away that the relationship between the contravariant vector of the old coordinates and the new ones is this particular Jacobian. So this sets the Jacobians up very automatically. And so that means, and this is something I didn't emphasize when we talked about this, is that the coordinate themselves, the v super m, the contravariant coordinates of a velocity in this case, and the velocity is indicated as something that's invariant. The velocity we're talking about up here is just for this device, and we're just looking at it differently in this coordinate system first. That's the theta and the phi, and then we're looking at it in the barred coordinate system, or the beam relative coordinate system. So the definition of a contravariant component is the dot product of this invariant velocity, and the idea is that EM right there, so I've got this, that EM right there is this this is combination of the E bar M, so you simply stick that in and you get a same transformation coefficient for the components of that vector, which is what you're interested in, as you do for the abstract vectors, the contravariant vectors. And the same thing goes for the other side of that if you're going to work with the covariants. Now the covariants are the momenta, you see. So the covariants, the index down instead of contra like these guys are right here, same deal. You saw it apart, and then you sum over the new coordinates, the barred coordinates, and you get that the old is given by new, and that's the coefficient. It's just a flip of this one, inverse of this, so to speak. Okay, and that then gives you the same coefficients that will take your transformation momentum, which we're seeing here. So this matrix and this matrix right here come directly from this formalism. They do turn out to be the transpose inverse. So if you're using matrices to do the transformations, and that's important because, as I say, most of this stuff winds up on a computer. Computers do things most efficiently by arrays. So here's the array that you would actually have a program if you were following this formalism to make our dynamics. So this guy right here that takes the barred components, that's the B guys right here, that's the same as this. Okay, just different notation. This is abstract notation, this is the notation that we're using. And the same thing goes when you go the other way with the momenta. Okay, this is the typical having the barred momenta here. This is the Jacobian that's right here, given by this. This is just notation, general notation. This is notation for a special thing. Okay, so that is an important piece of formalism. But this is a piece of everything that has to do with physics, right? This is really important. And I want to emphasize that one time again. I've already talked about this earlier in connection with saying Poincare invariance is really crucial, okay? Recall lecture 12, the last lecture before we started complex variables. Page 50, discussion of the differential action. That's what this is part of. The whole thing has got the energy, which is constant for a Hamiltonian, and differential in time. But this part right here, momentum times velocity, dot velocity. Okay, that's what we have here. Two views, two different views, beam relative view, the laboratory view of the momentum dot velocity. Okay, and that comes down to, this is v dot dt, that comes down to differential in space. So what we have here, when we're talking about the differential of combinations, and this is just part of it. We leave off the energy times time, but when you go to do relativity, you can't do that. This is a relativistic invariant right here, and it is the phase of the quantum wave function, you see. So the invariance of the phase is such a crucial thing. We're talking about here a simplified, very simple plane wave, but the fact that all little clocks, all little phase, whatever trackers, no matter who looks at it, no matter what you're doing, if it was a relativistic problem, whether you're going fast this way, going fast this way, or actually in the laboratory, all of those things would get the same phase. And this is something that's really, really crucial. This is the heart of the connection of classical mechanics to modern physics, which we will attack again at the very end of this class. But I just wanted to see you, there's some important formalism here, but there's also even more important a philosophy or a background that makes quantum mechanics work as well as relativity. They're really the same subject when you look at them in the right direction. Okay, back to the Trebuchet, back to the 12th century or the 15th century, depending on what era of war you were talking about. Here is the Hamiltonian with its denominator that goes with this, and then there would be a potential, that's the gravity. We've talked about having that, and now what we're going to do is we're going to consider just the kinetic part of the Hamiltonian, but this is potential would be there if it was this problem with gravity turned on. So here is the this thing written out now, p theta squared. So it comes out, this is our momentum transformation. And then there's p phi, but it's just the same as the momentum, the bar momentum. So we don't have to do any change on that. And that appears right here. So anyway, what we got is a Hamiltonian, and if we can not worry about the potential, we've got something that we can solve quite easily. And going ahead here and putting up some other things. This is using the coordinate transformation to the part. But you'll notice that what we got here with this is that the theta momentum is the difference between theta and phi, and that's not an easy thing to visualize. So, however you make whenever you make a contact transformation that involves momentum, you have to really be careful to make sure that that holds there. Now, let's see if there's anything else I need to say at this point. I think that is all, because now we're going to do what we did with the first physics that we did in this class, which is the super balls being dropped in gravity, hitting and causing some change in momentum. And we're going to here do a similar thing. There we could ignore gravity in the during the collision because the forces were so much larger than gravity, and so that allowed us to not to worry so much about it. But here, I'm imagining that some impulse has come and gotten both of these momenta going, and the idea is if we have this removed from the Hamiltonian for zero gravity, it's not a function of theta b. That means partial theta b 0, and time derivative of it is 0. So we have a constant that we can stick in for that. So there'll be a lambda there that is constant, and Hamiltonian, by definition, whether we have the gravity or not, is a constant. Okay, so that's the game we're going to play here. The same game we played with the super ball business. Now, let's see if there's anything else I need to say here. I did I want to go back real quick on this one and just emphasize that this relation right here, this is the transpose inverse. That's what you have to work with. This has to be the transpose inverse of that, and vice versa. That has to give one. Okay. Crucial. All right. Okay, let's go ahead here. We've got to replace a few things here using those transformations, and then we can do the algebra that's shown here. Okay, then most algebra is about to come. We've got to work this thing back and solve it by quadratic equations. So we're going to rewrite this as a quadratic equation in the angular momentum of the throwing beam, the phi here. We really mean phi b, because that's the system we're working in right now. We'll have, go and write a b on this thing. That's what we want to see. We want to see how much angular momentum, how much speed do we get in the throw of, I guess we might as well just call it the Chinese trebuchet, the one where a huge number of warriors go jerk on the thing and throw. So we're going to see what's the result of that. We're going to make an analogy of that with the super ball. Big ball, little ball, hits the floor, comes back and pops, right? This thing is going to pop. We're going to see how much it pops. We're going to solve for that angular momentum, P, phi, beam relative. Okay, so let's go ahead here. We have to rearrange this into a quadratic equation. That's what's going here. I stuck in the constant of the beam angular momentum, the thing that goes with the theta b right there. Okay, but we're going to be going after that guy right there. So we're going to have phi sub b in various places on this equation. Now, I have taken the denominator that comes from having a contravariant thing and an inverse, so that piece of algebra that makes a mess of equation making. For equation solving, it just goes to the right-hand side of this particular equation. And let's see if there's anything else here. I think most of this is fairly obvious. And we've got, let's see if I took that EML squared. Yeah, that's right. That seems to be it. Okay. So, in any case, make a long story short, we end up here with the quadratic equation, a big thing here called, this would be A, unknown x squared minus B, unknown times first power, and then a constant. Okay. We have to solve that thing in order to get the momentum, the throwing momentum, P sub phi. Okay. So, let's see if we got anything here that needs to be said. I'm going to keep this thing going on the same speed here. Okay, I think that's all there is. So, this is the answer. Basically, we've got a quadratic equation here, good old minus b plus or minus b squared minus 4ac, okay, and there's b squared, and then the whole thing divided by 2 times the a. The a is the coefficient out here. I've shortened it by having, first of all, a weird kind of sum of inertias, inertia of the main arm here, the inertia associated with that little m times this distance right here, r of the beam squared. It's little r, and then big R is the little distance, but that's attached to a huge mass that's driving, that would be driving this if this were a gravity trebuchet. Instead it's a Chinese trebuchet, and somebody has grabbed a hold of that thing and pulled it. And this term right here is a similar thing. It's the I divided by the inertia, rotational inertia associated with the lever arm. So we got to put those in there, J beam ending up there and I ending up there to simplify the equation. So that's what we're working with. Now the question is, how do we make any sense out of that? This is just going through the thing again real quick. Total kinetic energy, forgetting about potential. The old momenta p phi and p theta are there. We've discussed that there's a transformation between them to make this graph, and then we did all of the covariant contravariant to get the relationship between the old momenta and the new momentum, the beam relative momentum. So here's where we put it to work. This is just an expression, I'll get one more time, of those two. And one thing we're going to do here is make it a little simpler. We're going to make it so that this arm here is the same as this one. So L and R are going to be equal. Okay, easier algebra. We've got enough algebra as it is. This will make it a little better. So we're ending up here with expressions involving the old angles, theta and phi, and the dots, the phi dots there. Okay, so what we're going to do is imagine we're riding the beam. We have a starting point where the trebuchet sits ready to fire. We might as well break the boredom here. I'll actually fire a trebuchet, or at least I'll try. Let's see how it goes here. What I'm going to do is I'm going to take this guy right here. It's got a lot of washers on one side, and I'm going to cock it. That means I'm going to put this thing so that it will come loose. In this case, we're going to throw the little lever arm L along with the projectile M, little m, lowercase m. So here's or it will be, I hope, a cocked trebuchet ready for business. And it's headed kind of that way. TC may have to duck, but he's got the camera on it. Let's see what happens. Well, that time it hooked, didn't it?
Yeah, it jammed up.
And usually I can get it over the end of the table, but you get some idea what it is we're talking about.
Try one more time, because the second one worked
Yeah.
flawlessly the last time.
I
I'll
will
put you on the spot.
put it closer to the end and hope that that works.
Now, I've seen illustrations where the more ancient mechanism would have a loader who would hang on it while everybody else was yanking over. Of course, he'd let go, or she, you know.
Yeah, we'll talk a little bit later about the history of these crazy machines. Let's see if I can get that to go there. All right. I'll try. Let's see if it goes. Ready, aim, fire. All right. That's the best I can do with this
Let's get it up by
toothpick
3 orders
trebuchet.
of magnitude.
Yeah. There's another one here you can play with after class. It doesn't, the attempt of putting wheels on it, that was actually what the trebuchets that did battle had. It turns out if you have a really good beam, and this one doesn't, it actually moves forward. So it's like the pitcher pitching and also translating, adding an extra 5 or 10, 20 miles an hour to a pitch that's already 90 or 100 miles an hour. So anyway, what we're going to do is we're going to start with the thing completely tucked in. Then we'll call that 9 o'clock. And then the next we'll talk about 6 o'clock, where it's at 90 degrees. And finally, by this time it will have gained a certain amount of velocity just from the motion of the beam. Beam goes moving, where beam relative pictures right there. So the idea is to take this equation apart, and the basic idea is to look at the different cases, and we'll start with 9 o'clock using these equations. So we have 2 times the total energy, this thing in general, and the total angular momentum is this lambda here. Both of those regarded as constants throughout the motion. This is what we've been given by the Chinese warriors that have put the thing into an angular thing, and then it's going to open up. Okay, so starting with the 90-degree, well, starting with 9 o'clock right here, that's theta b, beam relative minus 90. the phi b given by this equation, and remember we're making it so that this thing is actually exactly as long as that, and then we take that this value here using the numbers we have, so we end up here with these two angles at the starting angular velocity. So we start them rotating exactly together, and then this one's going to gain speed in the process. So that's the thing. Then at 6 o'clock, where the thing is out, they're having the most acceleration, but not necessarily the most velocity. That's what you get for that particular value of phi b. 0 degrees right on the perpendicular to the beam. And then finally phi b plus 90, this is where you let her go. This will be the place where the speed is maximum. So that's the what we're doing here, and we have to make sense out of these the equations that we have here, and that is a little bit of an effort. I'm going to go ahead here and put down just what it is we have. This is the mr squared. Well, this is the kinetic energy really of m as a function of the angles, and then this is the 3 cases, and the last one is the sum squared of those two phi dot and theta dot. The lab velocities are there, and the beam relative thing has changed from minus 90 through 0 to plus 90. So all of those together give us an equation that we can. Now, what I'm going to do is take this guy right here. This is the one we're interested in. Let's see. This is the one we're interested in. I'm going to take this one and divide by mr squared and subtract. So I'm going to end up exposing the omega squared here. Divide that out, and I subtract this phi dot squared, and end up with a sum squared of the velocities at the pi over 2. That's this thing. And that takes care of the kinetic energy. See, this was the initial KE. Now it's still the same total kinetic energy. Same thing with the initial angular momentum. That is same numerical value, but algebraically it has this. So this is where we get the answers. And then divide that by, just divide this by that. So we have omega squared minus theta dot squared. That's omega minus theta, omega plus theta. Omega minus theta cancels, so we get an omega plus theta. And then this thing has a similar thing that lets us, since these are both the same quantity, this one's squared, that just leaves me with a linear expression here for the final, well, we can turn it into one for the final velocity. What we get is phi dot is equal to theta dot, that's the beam velocity, plus 2 times the omega, this omega that was put in there initially. And you see some equations emerging that are reminiscent of the algebra for the Super Bowl collision thing. And go ahead and substitute that thing in and divide that out. I get an expression here, omega for minus 4mr squared. In any case, solving that gives me the theta dot. That's the beam. The beam is going to be, so this would be analogous to the speed of the lower superball, and then the pen, or smaller superball that sits on top of it, is going to be described by that expression there. Okay, so we're almost done here. We're almost in a position where we can think, make some sense of it. Now recall in the super ball case, we had still on the board over here, we can look at it. We had a case where the momentum, the mass of the lower ball was large, that is, the slope was large of the ratio of the large mass to the small mass. So what we got then with our geometry was a final velocity right here of 3 times whatever it came in with. Okay? Remember that? And then I said if nature was unkind, every little piece of sand would come back at you with 9 times with kinetic energy. Okay? Anyway, that 3 showing up here. Showing up, you see it there, right here. Okay? And the final beam velocity is exactly where it started. So this is the case where the trebuchet is throwing something really light, very light compared to the drive, to the rest of the machine. Okay. Now we had another situation, which was where we got rid of all of the kinetic energy of the lower, the M1, the big M, okay, and put it all in the pen, the thing that went in the ceiling, okay, and we left the velocity of the pen then was 2 times what it started with. Kinetic energy then 4 times what we started with, as opposed to 9 times up here. But in this case, the driver ends up with 0. Okay, with 0 momentum. So I go ahead and put that one down here as well. I call optimum. Here's where you, to get this one, you make the big R, but short r, M short r squared, big M short r squared is equal to 4 times the little, but not negligible mass, little m, this r squared, okay? And lo and behold, here's the phi dot, that's the ball flying off, with twice. Exactly what we got here. Okay? Isn't that wild? I'm amazed by this. And I still have not, gotten an easy way to see why that is. There's got to be some symmetry or something going on in this, but I find it really quite beautiful. So we're talking about these 2 extremes, right there and there. And they're very analogous to the thing. Now there's some more. If you look in Unit 2, if you're interested in exploring this little thing that happened, and here's the, well, first the reference is Scientific American, which got me started on all this is back in '95. These are the guys that did the project, or they were part of the project, a major part of this project. And that was in Smithsonian Magazine. But there's some links to the PBS program that shows them building that. And what I noticed was that if, for 100% energy transformers, that's really what they were achieving. If they had a mass ratio of 50, and as I say, these ingeniators, by the way, the name engineer comes from, this was called the ingenium, and the people that ran them were called ingeniators, and finally the word engineer comes out of this. It took a few hundred years for that to happen, but It's an interesting piece of history. Anyway, they had 12 to 13,000 pounds of lead and sand. That's what they used. That lead in 1215, when this siege of Kenilworth occurred, guess where that came from? The roofs of all the churches in the neighborhood were torn off and made into the mass that was driving the trebuchet for the siege of Kenilworth. I mean, it's a horrible history. I mean, it's just nasty, right? But anyway, assuming that, using this formula here, I figure the ratio between the big R, which is the little radius, and the little r, which is the big radius, that ratio would come out to about, well, 50 over, square root of 50 over 2, 3.5, according to our formula there, okay? And instead, drawings show an L of, well, 42 feet, that's about 3.7 times the driving radius. So they have a little longer throwing arm and R, which were about the same. And it has to be that way because it has to clear the thing. So it is larger. But anyway, this comes out to, you know, about right. So we can use this. And we can also figure the speed that they were getting in the throw. And it's similar to what our the computer simulations, but the idea that we get 94, they actually achieved something between 100 and 120, according to the references. So, okay, that's the story of this monstrosity, as far as I know about it. It's quite a tale. I emphasize that this guy right here really does a good job of throwing that thing, much better job than normally. I'm going to see if I can get that to work. I've got both of these supposedly on the web, so let's remind ourselves of what this one was. That guy really throws the thing out there at a I'm talking a velocity 144 in this particular example. Let's go back. Now, I haven't told you all the history of this terrible instrument. This was the typical omnipotence one, which we've looked at already. What I would point out to you, and this is just a picture that comes from things, not actual, not a working one, but if you click on this, you get something like that that we just saw. But what happened much later, and this is after trebuchets just weren't used anymore, cannons were beginning to do warfare far worse than the trebuchets. But there is a claim, and this is somewhat disputed. Some historians say this did happen, some say I've never heard this. Claim is that Cortez built a trebuchet to lay siege of Montezuma as they were doing what the white man seems to do, and that is screw up the rest of the world. But Montezuma went into hiding and had lots of buildings, and so these guys built a trebuchet right there, chopped down trees or did whatever it took, and got rocks, or plenty of rocks, no lead. They might have used some of the gold that was there, but anyway, they built a trebuchet, and according to the report, this is what happened. First try, just to see if it was going to work. Okay, they destroyed it on the first shot. Okay, that's what the history of this. So this is the death. If it happened, this is the death of the trebuchet right here. Never used except for now. We're doing it in Oklahoma every Halloween. We throw pumpkins with it. Okay. So, all right, that's the sort of the end of the description of this particular device. And here's pictures of all of that. But we really owe it to ourselves to talk a little bit about this, because this is not killing things. This is building things. This is mostly here, and as I say, reaping the doing that, and doing it so that you don't have to go see the orthopedic surgeon, because in the 9th century or before or after that, there weren't any orthopedic surgeons. You had to do this right, and it's true for all of these other things. You had to learn how to get that kinetic energy into those, whatever it is that you're hammering or holding, digging, splitting. The woodsman would be doing that, okay? And as I say, every one of these has an analog for recreation. The kinesiology of this is the same as, pretty much the same as the kinesiology of this. Right down to some extreme examples, like our slingshot to get us to get our instruments to Jupiter or Saturn or Pluto. You had to do basically a slingshot, okay? Basically, and I mentioned the bullwhip, okay? This thing, the cracking of the whip, where this end actually breaks the sound barrier, okay? Makes a sonic pop, okay? A crack. And you probably may know that the Spanish ranchers used the bullwhip to whip the cattle. I mean, that was the way they rounded them up, okay? And the people in Florida are called crackers. Have you ever heard that? Okay, that's where it comes from, the crack of the whip. Okay, they're driving their cattle. Okay, so anyway, talk a little bit more like this at the very end. That's a whole nother story. But here, I'm just showing you one thing that's really important about a trebuchet, and this is just talking sophomore physics, is that when you first let this thing go, you get a really big pull here, in which the force, and the force can only be along the lever arm L that we were talking about, which is a string in the case of the one we demonstrated, and that force is pretty much for a long time in the same direction as the V. So the velocity goes up very quickly in the beginning, and then after that it's sort of maintained, and mostly the force is being used to steer the mass, okay? So early on, later on, are very different things in regard to this. And the idea of that is that when you talk about swinging a bat or a tennis racket or something like that, the idea is to put kinetic energy into whatever it is, say a tennis racket, that's what I swing a lot. The idea is that once you have a hot racket, then it's not too hard to steer the thing if you've been going in the right direction to begin with. And in fact, you play a mind game where you imagine that you're going to hit the tennis ball with the butt of the racket. You're literally going to put the butt of the racket on the ball. And you do that, but you get a little bit above it, and the racket comes through at a great speed with very little effort. You're doing effort over a long period of time and distance. It doesn't take much force, you see. And this is why women play almost as with no testosterone as the men who have lots of testosterone. The women are hitting almost as fast as the men. And this apparently is true in baseball too. In fact, the pitchers and women are faster. The underhand pitch is faster than the overhand. Anyway, the way to learn what not to do with a lever is here. And this is the, what I call the flinger. Now the flinger, I ran into that with my sons who played with skateboards and also played pool. And every once in a while when a skateboard would fall apart, they'd take the wheel and they put it on the end of a pool cue, just slide very nice and had graphite so it was slippery. You'd put it down where it stuck a little bit, and then you just go fling like that. That's the opposite of the kinesiology of the sports, okay? Because early on, not much is happening. It's only at the very last minute you cram for the energy as you go out. So the velocity doesn't build up until the very end. And you can get away with that because it's a small mass and you've got a lot of oomph here. Now the trebuchet-like experiment, which we use to compare this is just to simply take the pull goose, saw it off, put a hook in it, and then hang the skateboard wheel on a string. So that's what I'm going to compare. I'm going to compare those two and see which one is really better in terms of, and we'll use the algebra of all of this to obtain that. But let's just go ahead and look at, real quick here, what the Flinger has to offer in terms of animation, and I hope I get a pretty good picture of it just by hitting this. Let's see if it works. There we go. Anyway, 56 miles an hour for this, but roughly the same geometry of this. This is very discouraging as far as getting kinetic energy into something. This is not the thing to. And people that start off with tennis and try to force the thing like that, it's not a winning deal. You see, the idea is to get way back here and get the kinetic energy into the tip, and not have to go to the orthopedic surgeon to replace your elbow or shoulder or whatever that you get from forcing things. So that's kind of the message that I am doing here. I'm going to pause this and get back to the thing where we discuss this in a quantitative way. That's a deal. So here's the model I came up with. Now this model it's not good, because what we're going to do here is assume that it's always got the same omega, always. So this is a much simpler. This is the UP1 elementary physics approach to figuring out how well the Trebuchet does, which can start here at 9 o'clock, go through 6 o'clock, and come out here. But it can also start right here, so it's more like this one, which starts here at 6 o'clock. That's sort of equivalent to what this one has to start at to have the same sort of distance to gain. Now this one is going to be gaining by a centrifugal force that pulls the thing out, just as this one is too. So at first you might say, hey, this is a winner. It just goes directly to the centrifugal barrier. The centrifugal barrier for this rotor, okay, is an upside down parabola. You're just looking at the potential energy due to a centrifugal force, okay, and this thing right here, this potential is the integral of the centrifugal force, which is linear in R, so this is quadratic in R, and in fact that's exact potential for the centrifugal barrier that's going to get you to get up to speed. So we're going to be figuring out how much it gains. We're going to be doing a similar thing with this one. This thing is also experiencing the centrifugal force. So basically we're going to be looking at the kinetic energy. This is in the beam frame where we're with this thing rotating always at a constant omega, and doing either a flinging or a trebuchet. This is the trebuchet comparison. Okay, so the idea is to see, how do these match up? How much energy do you get in? And this one has a final here. And what we're doing is we're saying this final trebuchet kinetic energy should be whatever you get from starting with your potential at this distance, RB plus L, okay, quantity squared. We're talking about that distance right there. And this is the final minus the initial is giving you this much kinetic out of that. This one a little bit different. It's the final same as this one, but the initial is just RB squared, okay? So you start off at RB squared, which is that distance, and you just fall down the thing. This one's more complicated. You start out here, same projected radius RB, but actual radius this, and so that is what you're going to be comparing. You're going to be comparing the final that you would get by having R plus L squared from what you get by having a Pythagorean radius of hypotenuse r squared plus L squared, okay? So that's the difference of these two things gives me that. Well, this one is kind of weird, it gives me that, so how do they compare? Well, we have to put the numbers in to really see that. This is the final 3 o'clock, initial 3 o'clock, it's always at 3 o'clock in the beam frame, okay? So I'm getting there 2RB plus L. Here I'm getting 2R times L, okay? But this one has an extra L, so maybe it's winner, okay? The disadvantage is that the kinetic, well, to make a long story short, the kinetic energy for this one, this is if you use a 9 o'clock thing. Let's look at the numbers, okay? Over here, half clock, that's 6 o'clock, okay? Fully clock, 9 o'clock, that's what you should really do with a racket, and that gains you some. But the half clock, you can compare, let's see if this is right here, yeah. You can compare these two, okay? And this is a clear winner. This 6-to-4, basically, ratio of this one, okay? And the advantage of this one is that if you've been aiming correctly, this one comes out at a velocity that's at an angle to this. It has a velocity already this way, but then it's got the body velocity to add, so it ends up coming out at an angle, like you might have noticed in the simulation. Okay, so this is a comparison that really shows that you get a heck of a lot more from this, particularly if you go fully clocked with at 9 o'clock. But even at 6 o'clock, it's a winner. Okay, so we try different radii too, just to change. Anyway, that's what this is something that we'd really like to make a machine to experiment with. We just haven't gotten around to doing it. I like to make a comparison now as you guys go into the field of physics. It used to be it was bipolar. You had a theory and then you had an experiment, and almost these guys hardly talked to these guys except when they were trying to get them to do something, and these guys hardly talked until they got stuck, and they would talk to these guys. But that system has really changed. I've watched the transformation. It's just absolutely amazing. And the reason it's changed is because we don't just have lab and theory. We've got this kind of theory. A computer can make a graphics of a Trebuchet or whatever you want to make. Okay, so as I've always said, the art of approximation is important. But when it comes to mechanics, the stuff we're doing in this class, I wanted to emphasize that this is an international effort. And here are the characters that are most known, I would say. Of course, we're in U.S., so naturally that one gets the most attention. But don't forget Lagrange and many others that we'll talk about later on, and other sorts of things. We haven't done much yet with this one, the German approach, which will be the Riemann-Christoffel equation, which is right in the center of the equation section over there. And then you've got to give credit to, this is the most powerfully creative bunch of people, the Anglo-Irish. That's Hamilton. We're going to hear from Hamilton for the rest of this course. So altogether, Hamilton, Jacobi, I'm not sure about nationality, Poincaré definitely French. So that's what we're living with now. And the idea is that get all this stuff working together, we're making progress like we never have. Well, this is what I call a cheap trebuchet, and I'm going to end the lecture right now with that. And any questions or whatever, please bring them up. This is, I think, interesting stuff to make a connection with all this algebra that we do, calculus and everything, and real world. It's out there, right? It's in here. The other thing I would point out was when I talked about the Poincare relation and the relation to the phase of the waves that we'll be studying both for when we do relativity and quantum mechanics together, the question immediately emerges for anybody that does quantum mechanics, which we do, that there must be a quantum trebuchet. I mean, you have a classical mechanical device that does this. Turns out there is, and it's all over the place. There are lots of floppy molecules that have an entire methyl group that's rocking back and forth as well as turning. And every time you move a muscle, just go like that, the muscles that did that, the strands, have little trebuchet motion as it takes the proteins or whatever up a strand to make it contract, to give the energy to contract. So it's so just as I do that, something was going really fast up and down that fiber in order to make the muscle contract. So we already have inside us quantum trebuchets, or very nearly quantum. They're macromolecules, but you're in the molecular regime. And quantum mechanics begins to have an influence, at first not noticeable, but then later it gets more noticeable as you do more careful experiments. So there's a lot to learn from the trebuchet. It isn't all bad. Okay, well, we'll see you next day, Wednesday, on some other topics.